So far, we've been exploring one of the fundamental building blocks of linear algebra, which is matrices, and the way that they correspond to linear systems of equations. Another fundamental building block is the idea of a vector. And we're going to explore vectors and vector spaces a lot, and we'll see how they're related to matrices. So today is our chance to meet vectors. And if you've done physics or even other math classes before, you may have different ideas about what vectors are. For us in this class, we're going to keep it pretty simple and just say a vector is an ordered list of numbers. Order just means that order matters. So 2, 3 is not the same thing as 3, 2. We will often write them as a column matrix. So that means a matrix with a single column. So for instance, something like 2, 3, or -3, 1. I don't have to have two entries, of course. You could certainly have a vector that has lots of entries. So if they are two-dimensional, though, they can be graphed. Just by looking at the first component as an x and the second component as a y. So let's take a look at graphing like 2, 3 and -3, 1 and maybe some combinations of them. So let me point out first of all that vectors have a few algebraic properties. These are listed in your book, so I don't want to go over them in excruciating detail. But let me just point out here what they are talking about when they write these properties down. U, V, and W are all vectors. This Rn means real space in 2 dimensions or 3 dimensions or 5 dimensions. So R stands for real numbers, so no complex numbers. The N stands for how many entries it's going to have. So when I was writing down 2, 3, oh yeah, right layer. When I was writing down 2, 3, that's a vector in R2 is the way we'd write that, because it's 2 real numbers. And scalar just means, scalar is a fancy word for constant number. So I'll just say number. So something like 5 or -3.7. So they're pointing out that a lot of our basic algebraic properties hold here, like addition is commutative and addition is associative, and if you add 0 you get the original thing back. And if you add the positive and negative of the same thing you get 0, and so on. So just wanted to point out that a lot of those normal properties hold, so we'll make reference to those from time to time. But let's go ahead and look at graphing a couple vectors. Let's see, let's go to, let's get some graph paper up here. And let's see, I had 2, 3 and -3, 1. I'll just stick with those for fun. So let's see if we have, let's give them names. So let's say that U is 2, 3 and V is -3, 1. So we can certainly graph U by starting at the origin, going 2 over 3 up, put a little dot right there, and then the typical way to write a vector is as an arrow starting from the beginning and pointing to the end. So it sort of points out the distance traveled of 2 over and 3 up. So that'd be u. And then v, of course, would be negative 3, 1. Right there. So v looks more like this. Okay. Fair enough. So let's talk about some linear combinations. So let's say we wanted to graph. Let's just start off easy. Let's graph u plus v. Numerically, when you add vectors, you add them component to component. So u plus v numerically will be 2 plus negative 3, which is negative 1, and 3 plus 1 is 4. So we're just talking about the vector negative 1, 4. Let me plot that in with another color. So negative 1, and then 1, 2, 3, 4 up is about right there. Negative 1, 4 looks about like that, so that would be u plus v. Notice we could probably have done this graphically without even figuring out the numeric answer. U plus v just says go where u tells you to go, so go here. And then that's your new starting point. From there, do what v tells you to do. And v tells you to go 3 back and 1 up. So we could have just said, could have said, let's go u and then let's go v. And that gives us this same final location of negative 1, 4. So that's sort of a graphical interpretation. When you graphically add vectors, it's always going tip of one to tail of the next one. Or some other people want to say that if you plot u and v and then finish the box, right, make a parallelogram out of u and v, the other corner is the addition of u and v. Okay, let's go on and let's just try one more. We should be able to do something like 2u plus 3v. We should be able to do this both graphically and numerically. Let's try doing this one graphically first. So let's do 2 u's. So u says start at the origin, go u, which happens to be 2 over and 3 up. And then it says go u again, 2 over, 3 up. So that's u plus u, or just 2 u's. And then we also, so there's the 2u, and we added those tip to tail. And now we're adding 3 v's onto that. So v takes you back 3 and up 1, so back 3 and up 1. There's 1 v. Second v would take you back 3 and up 1, so there's a second v. And so we're going v, v. And the third v that we're adding on would go back 3 and up 1, so take you to right there. So the ultimate result of starting at the origin, traveling 2 u's and then also 3 v's, takes us from the origin to about right there. Let's pretend that's a straight line. There's a little bit better straight line. Anyway, that's what it looks like graphically. We could also figure this out numerically. So 2 u's and 3 v's. Let's work that out. 2 times a vector, you multiply, a scalar multiplies both components. So 2 times 2, 3 would become 4, 6. And 3 times negative 3, 1 would be negative 9, 3. So notice the scalar multiplies both parts of the vector. And then when you add them component by component. So 4 plus negative 9 would be negative 5. and 6 plus 3 would be 9. And now we know the numeric components for where we already traveled to. It is negative 5 over, and it is 9 up. So your homework's going to have you do some practice with combining vectors, both numerically, a little bit graphically. Graphical is easy to do in 2 dimensions, but as we move further on in the course, there's not much that we're going to do that's really in 2 dimensions. Oftentimes we'll be in 3 dimensions, we'll be in 7 dimensions. It's pretty hard to do that graphically. So at that point, we'll just rely on our numbers and on our conceptual understanding of what's going on. In the next video, we're going to connect the dots. We are going to show how vectors and systems of linear equations are fundamentally related.